Alright, welcome to this video on matrix theory. In this lecture, we'll be talking about projections and their connections to least square solutions. So, what do we understand by the projection of one vector onto another? You've seen this in high school and in your undergrad, that the length of the projection of a vector u onto another vector v is simply equal to the length of u times the cosine of the angle between the two vectors, right? And in general, so the orthogonal projection of u onto v, pictorially it is this vector over here. So basically we can write u as a sum of two vectors, u perp and u parallel, where u parallel is a vector which is parallel to v, and u perp is a vector which is perpendicular to v, right? And the length of u parallel is basically equal to the magnitude of u, or the length of u, times the cosine of the angle between the two, right? But what is this equal to? What is cos theta equal to? So cos theta is simply equal to u transpose v divided by the length of u times the length of v, right? So the projection, or the length of the projection of u onto a vector v, is equal to u transpose v divided by the length of v, right? Just by cancelling these two terms out. Okay, so let's see what happens in two very extreme conditions, right? So the case where theta is equal to 0. So, or in other words, if u is parallel to v, then what happens to the projection? So this is equal to u transpose v. So suppose that, so in this case, what is u transpose v divided by the length of v? How do we calculate this? So let's assume that since theta is equal to 0, or u is parallel to v, we can write u as some alpha times v, right? And therefore u transpose v is equal to alpha times v transpose v divided by the norm of v, but this is simply equal to alpha times the squared length of v divided by the length of v. So this is equal to alpha times the length of v, which is equal to length of u, right? So when theta is equal to 0, the projection of u onto v, or the length of the projection of u onto v, is equal to the length of u itself, right? And when theta is equal to pi by 2, that is when u is perpendicular to v, we have u transpose v to be equal to 0, and therefore the projection is also equal to 0, right? So all of this is fine. So you clearly know what the projection of u onto a vector v is. Now the question is, what about projections onto more complicated sets? So suppose we are given an arbitrary subspace v1. So v1 is a subspace of v. Then what is the projection of an arbitrary vector u onto v1? So that's the question that we want to address in this particular lecture. So firstly, what do we mean by a projection, right? Now, a very formal definition of a projection is basically a linear transformation from v to v or v to v1 such that t times u is equal to t square times u. So basically, if you take the projection of a vector and take the projection once again, then you get back the same vector. So basically, if you take a vector u and then take the projection onto u, and then you take the projection once again, right? You take the projection out of u and then you take the projection once again. So this is t square u, then this should be equal to tu. Just going by trying to extend the point over here. So if you take u and take the projection of u onto v, then you get u parallel, and the projection of u parallel onto v is u parallel itself, right? So of course, so any linear transformation or any matrix T which satisfies the property that T square is equal to T is said to be a projection matrix. And in particular, the matrix T is said to be a projection matrix, or is said to be a projection onto a subspace V1 if the range of T is equal to V1. So we'll see this in a little more detail now. So firstly, so even before that, let's look at one-dimensional subspaces. And what is a one-dimensional subspace? A one-dimensional subspace has basically one basis vector, and it is basically projection onto a line or onto one vector. So we already know what the projection onto a line is. So if v is any vector on the line, then the projection of u along the direction of v is equal to the direction of v, which is v by the length of v times the length of the projection, right? So the length of the projection is norm u times cos theta, right? Let's expand this out a bit. So this is equal to v by norm v times norm u times v transpose u divided by the length of u times the length of v. So cancelling out these terms, we get that this is equal to v times v transpose u divided by norm v squared. But I can write norm v squared as v transpose v. So this is v transpose u divided by v transpose v. So let's group some of these terms together. So let's look at this times u, right? So what kind of a transformation is this? So this is a map. So the map v transpose divided by v transpose v, right? It's a linear map because v transpose is going to be a matrix. So if v is a length n vector, then v transpose is going to be an n by n matrix, and v transpose v is just a number, right? And this is a linear transformation which depends only on v. So this is some tv times u, and it's equal to the projection of u onto v. Now let's first check that it indeed satisfies this definition of a projection, that t square is equal to t, right? So let's take v transpose by v transpose v whole squared, right? So that is equal to v transpose divided by v transpose v, which is equal to v times V transpose V times V transpose divided by V transpose V the whole squared. But V transpose V is just a number, right? So I can take it out. V transpose V times V transpose divided by V transpose V the whole squared, which is simply equal to V transpose divided by V transpose V. So this is indeed a projection matrix as we saw over here, right? Okay, so this is the projection onto a line. Now let's see how to find the projection onto an arbitrary subspace. So suppose that we have a subspace V1 of a bigger vector space V. Then the projection of any then the projection matrix is basically going to be, it's a linear transformation, it's a matrix which has to satisfy the following properties, the following common sense properties. So firstly, obviously if you take any vector u and try to project it onto the vector space V1, then the projection should obviously lie in the vector space V1. So P times u should be in V1. And secondly, if you take any vector which is already in the space V1, then you should get back the same, and try to project it, then you should get back the same vector. So P times u should be equal to u if u is in V1, right? So these are two basic properties that we want any projection matrix to satisfy, right? And this obviously makes sure that, so this second condition ensures that PV square u, so PV square is equal to PV. And why is that? If you take PV1 square times u, then this is equal to 1. Okay, so if you take any vector u in the vector space, then PV1 square u is equal to PV1 of PV1 u, right? But we know that, but from property 1, P of u is already in V1. So this term is in V1, and therefore PV1 of this quantity is equal to this is equal to the same thing. So this is equal to PV1. So basically we are being consistent with our earlier definition of a projection matrix, or basically a projection. Okay. So this is a very abstract definition, and we need to make this more concrete. Okay, so I claim that if we have any vector space V1, then basically the projection onto V1 is given by the least square solution. And what do I mean by that? So since V1 is a subspace of V, then you can write it as the column space of a full rank matrix A, where the columns of A basically represent the basis vectors of V1, right? So this is full rank, right? And we'll assume that V1 is a strict subset of V, right? So the dimension of V1 is strictly less than the dimension of V, right? So to put things in terms of Rn, we can take V1 to be some arbitrary subspace of Rn. Assume that V is Rn, right? Okay, so let's take this to be Rm, and we'll assume that A is an m by n matrix, right? and obviously for this to be full rank, and for V1 to be a strict subspace of V, we should have M to be greater than, or M to be strictly larger than N, right? Okay, so my claim is that if this is the case, if V1 is the column space of a full rank matrix A, then the projection of any vector u onto V1 is equal to the least square solution, right? So it is that vector A times x which minimizes the distance between AX and u, right? So this is equal to argmin over all A times x AX minus u. Okay, so firstly let us see why this is equal to the projection. Okay, is property 1 satisfied? So is property 1 satisfied? So the projection should lie in V1, and that is indeed satisfied because we are minimizing overall possible V1, which can be represented as A times x. So obviously V, the solution of the right hand side, is indeed going to be a vector in the subspace V1. So property 1 is satisfied. What about property 2? So what does property 2 say? So if we take any vector in V1, then P of u is equal to u, right? So suppose that u lies in the vector space, then what is argmin of what is this argmin equal to? It's equal to u, right? Because there is a vector. This quantity is obviously greater than or equal to 0. The right hand side is greater than or equal to 0, and it is equal to 0 if and only if v is equal to u, which obviously happens when u lies in the column space of A, right? So property 2 is also satisfied. Now are we done? Have we completely showed that this is a projection? There's one tiny step remaining which we glossed over, and that is PV1 must be a linear transformation, right? And from this formulation on the right hand side, it is not obvious that this is a linear transformation, right? Is the argmin a linear transformation or not? And the answer is, of course, it is indeed a linear transformation because it's the least square solution, and you know that the least square solution for a full rank matrix A is simply equal to, so this is equal to A times A transpose A inverse A transpose. So this is indeed a linear transformation, and PV1 is equal to A times A transpose A inverse A transpose. Right. So maybe let's see how do we get the least square solution. This has already been solved in as one of the challenge problems, but there are different ways to do this, and here is one particular solution of the proof. I won't go through all the details, but this should at least give you an idea of how one can solve this problem, right? So our goal is basically to solve this minimization problem, which is argmin of AX minus u, norm of AX minus u. But minimizing norm of AX minus u is the same as minimizing norm of AX minus u the whole square, because square is obviously a monotonic transformation. It's a monotone function, and therefore minimizing norm of AX minus u is the same as minimizing norm of AX minus u the whole square. And the advantage of working with this is that we can write norm of AX minus u squared as AX minus u transpose times AX minus u, right? So let's expand this out a bit. So we get x transpose AX minus 2x transpose A transpose U plus U transpose U, right? So this is our objective function, and our goal is to minimize this over all possible x in Rn. Right? So we want to minimize belongs to Rn of minus U squared. And there's another reason for working with this. Of course, we have the following nice looking expression over here for f of x, but also this is a convex optimization problem which we know how to solve, right? So we can take the partial derivative of f of x with respect to each xi, and basically what you get, if I write this in vector form, then this turns out to be equal to A transpose A x minus 2 A transpose U. And I leave this to you to, sorry, 2 A transpose A x minus 2 A transpose U. You can work it out by taking the by expanding out this matrix multiplication. So if you take any, so if you have any matrix B in general, then the partial derivative of Bx with respect to x turns out to be equal to B, and partial derivative of x transpose Bx, you should expand this out as a nice big summation. So it will be a double summation, and the partial derivative of this with respect to the vector x turns out to be equal to Bx, right? Okay, so getting back to the problem, we want to minimize f of x with respect to overall possible x in Rn, and we can do this by taking the partial derivative with respect to each xi and then setting these to 0, right? And basically what we get is that A transpose Ax is equal to A transpose U, or x is equal to A transpose A inverse A transpose U, right? So this is the least square solution, and therefore our V, which we wanted to find out, so V is equal to A times x, which is equal to A times A transpose A inverse A transpose U, right? All right, so to summarize, we've seen the connection between the projection and the least square solution, right? The projection of a vector or the projection matrix onto a particular subspace is basically equal to the least square solution. And you can also, I leave it to you as an exercise to verify that this is indeed a projection matrix. So p squared is equal to p, and that basically follows along the same lines of the proof that we did over here. Okay.